All right. I think we're ready to start the next session. My name is Kevin Pitstick, and I'm going to be co-presenting with Oren Wright. And we're going to be talking about software for mission. So again, who we are. So I'm Kevin Pitstick. I'm an engineer in the Tactical Technologies group. And I am a co-principal investigator for Summarizing and Searching Video, which I'm going to be talking about next. I also do some software architecture and development for one of our PWP's a TELUS project. Oren is a research scientist with the Emerging Technology Center, and he's PI for research in machine emotional intelligence and signal processing, and he'll be talking about that work in a bit. So to start out with, what do we mean by software for mission? So what we mean here is that we're doing software research and engineering at the SCI, not necessarily always for its own sake, but also to ultimately improve and add new capabilities to the DoD. You can sort of talk about the innovation gap where you have academic research happening on CMU's campus, but it doesn't always make its way over to mission deployment. And so that's where the SCI likes to insert itself to help apply this research to DoD problems. Going back to Roman's enduring challenges from the SCI strategic plan, we fall very much in the capable realm rather than affordable, trustworthy, and timely. To help make new missions possible or to improve the likelihood of success for other projects. You've heard a lot of talk about machine learning, and I'm going to reiterate it. We sort of consider, as we're going over our portfolio of software for mission projects at the SCI, we found a commonality, and that's that a lot of the projects involve transitioning machine learning research to the mission. When we ask ourselves why, we can sort of look at the AI stack. This is from CMU's website out of the computer science department. As you sort of work up this AI stack, you have the computing layer where you have a lot of the OS, the software, sort of the infrastructure. At the device layer, you're starting to get into sensors, things that capture the data. Then, of course, there's this massive data management layer where you have to worry about, now that you have millions or billions of rows of data, how do you manage that to effectively utilize it? And then really it's the machine learning stage that sort of enables you to go from sort of this layer of perception down here up to a higher level of reasoning. So you get to decision support as well as planning and acting. And so this sort of semantic ladder that Oren will be talking a little bit at the end of the presentation is really what we're trying to rise up with for machine learning. And then ultimately to provide these capabilities, autonomous capabilities, human-machine teaming to the warfighter. So we have two projects that we're going to go over. These are just two projects in the SCI Software for Mission category. I'm going to be starting with Summarizing and Searching Video, which is my team's project, and then Oren will follow with his project, Emotion Recognition from Voice, and then he will wrap up the presentation. So start off Summarizing and Searching Video. So this work originally began back in 2017 with another line project called Video Summarization. I'm going to briefly talk about that a little bit, and then has sort of morphed into 2018 with some additional work. But before I delve into specifics, I did want to go over briefly to sort of level set and make sure everybody is aware of aerial surveillance, and what we're talking about here. So you can sort of see this is This is a slide from an Air Force brief where they're looking at, over here you have full motion video where you have a lower flying platform that can really only see single targets or small areas. It also goes over to the right where you have this wide area motion imagery. You tend to have less frames per second, but you can see a much larger area. We're talking about electro-optical, so capturing the visible spectrum, but there's also a lot of work in the infrared IR range for nighttime operation. If you're looking at applications, they use these drones for situational awareness in battlefield. They use it for disaster assessment. California Air National Guard uses it a lot for assessing disasters, search and rescue, that sort of stuff. You can see this is an example of an image from a WAMI image. And then down here, this is one of the platforms, the MQ-9 Reaper. Other platforms include the U-2, Global Hawk, Predator, a lot of stuff that you've probably seen before in the news. So when we're talking about the problem that we want to address, so Brendan McCord yesterday did a great job giving an view of the Joint AI Center. And so one of the topics there was how the volume of DoD imagery coming in to be exploited is outpacing the ability of our analysts to do it. And so there's been an increasing push, as recognized in the JAIC with Project Maven. They've done a lot of work in how to reduce cognitive load on the analysts. Here's a good representative example of what this video looks like. This is a publicly released segment from CENTCOM. So you can tell it's not the best quality always. You have a constantly moving platform. These blacked out areas are actually sensor values that are shown. That provides issues for machine learning algorithms sometimes. And so really we're looking at ways that we can improve the situation for the warfighter. So going back to video summarization, the work started in 2017. We said, well, one of the things that we can do is work with the CMU ML department, and I have their collaboration listed down here. They had some work in how to take a longer amount of video and condense it to shorter segments. You can think of that as sort of condensing it to a trailer. And so the approach we were looking at was first really trying to identify the unique segments in a larger span of video. Do some object detection and tracking, segment those tracks into meaningful places, and then use some unsupervised LSTM autoencoder approaches to look for the segments of the video that are most unique, and then finally condense those into the summary. So here's an example of a summary. This is a 17-minute video that's been reduced to 5% or 51 seconds. We found that there were definitely some uses in triaging large volumes of video, but it really isn't something that you would necessarily be able to give to the analyst to support in real time. And so we decided that there were some other analysis techniques that we needed to look at for pulling like patterns of life out of video. So to move on to some of the work that we started in 2018, we started to look at a revised strategy of looking more at pattern of life analysis. And so the higher level goal is how we can utilize machine learning to enhance situational awareness and improve decision speed for the analyst. And so the basic idea is you have your aerial surveillance video coming in at the beginning as well as sensor data. These are things like yaw, pitch, roll of the sensor platform and other things that can help you in georegistering the objects. From that video, you can do a lot with the detection and classification. And you can get things like people, vehicles, and buildings. This is where a lot of the focus in the DoD currently is with Project Maven, so they're sort of at this layer here. Once you get those detections, then you can start to look at aggregating the objects, starting to aggregate the tracks, and start to do more pattern of life processing. So we're looking for what behaviors we can find from those objects and tracks. Once you have a sense of what the general behavior is in a compound, then you can start to look at what anomalies you might have. And then very further down the line, you might be able to start to make predictions of what these objects will do in the future. And the idea here is that we want to utilize human-machine teaming so that we sort of realize that the machine learning algorithms may not be able to take over the role of the analyst, but they may be able to work well with them to provide tips or cues, places they can look more closely into, and then also to provide summaries in creation of like PowerPoint products, that sort of thing. So going on to one concrete example, we did a little bit of work starting in the last few months about anomalous track detection. And so the idea here is that given that you have all the person and vehicle tracks, you can imagine GPS data over a given area, can you find people or vehicles who are moving in an unusual fashion? And so we utilize this Sumo traffic simulator and create an area over in the SEI CMU campus area where we were able to simulate about 1,000 tracks. And the idea here is, they're going from point A to point B. So you can imagine you're starting on Forbes Avenue, you're trying to get to Fifth Avenue, and you have these tracks taking the best path. In addition to that, though, we can say, well, what if we insert a track that maybe isn't optimal? This may be a guy looking for a parking spot. Parking's always rough. Or maybe, it could be a sign of, in an actual battlefield of worse behavior. And so this zigzag track some of the initial results we had is we had about 1,000 tracks that were analyzed in about 15 minutes, and we found that with the first few tweaks of the algorithm, we were able to find that the zigzag had the second highest score. Basically what you're seeing is the tracks are ordered in reconstruction error score. So the idea is that the algorithm learns the track pattern, and as you have a higher reconstruction score, that particular track has not been seen, or it has a less ability to reconstruct it. So it was very, so zigzag was the second highest score. We also found some additional anomalies that arise just from the randomly generated data. So we saw a vehicle that had long delays, traffic jam. So by using the LSTM long short-term memory autoencoder, it also looks at the temporal anomalies as well. And so this particular car was stopped 3 or 4 times in a traffic jam. There was also, if you're on one side of the road and you need to be on the other side of the road, we saw a vehicle that actually made a U-turn. So that is also anomalous activity that was in the top few. So getting into mission applications. So really the big mission applications that we're looking at are the DGS sites. So these are the Air Force sites who receive that aerial surveillance video and are able to analyze it for a customer. They're generally not the people who own the platforms, but they're providing a product. Marine Corps Intelligence, I mentioned before, California Air National Guard, they do a lot of work in this realm. What sort of things could these techniques be used for? Well, intelligence tipping and queuing. When an event happens in real time, notifying the customer that this is happening. Potentially aiding product generation. So there's a lot of manual work that goes into creating PowerPoints to give to the customer. There's a limited number of cases of forensic analysis, so sort of the anomalous tracks would probably fall more into that realm, where you have video gathered over, potentially a platform could be looking at an area for months at a time, and you have, thousands, tens of thousands, millions of tracks, and you need to somehow make sense of it and look for patterns. And then again, the human-machine teaming concept of, the goal is not always necessarily to replace the analyst, but to give the analyst better tools. And to help them be able to focus less on the layer of perception and more at the decision side of things. So to wrap up, project artifacts, I'd already talked a little bit about the video summarization pipeline. So we do have algorithms and code for doing a lot of this. We have a paper in a SPY on applying some of these techniques to aerial surveillance. Talking about the anomalous tracks, we have some initial algorithms and code using the simulated tracks, as well as trying to find the most anomalous tracks with an LSTM autoencoder, and then some initial test results with that. And then plan for FY 19 and 20. The project has a couple more years. We're looking at creating a larger data set with more anomalies. Zigzag is not the only anomaly you could potentially have, so there could be things like certain vehicles blocking traffic, or traffic needing to be redirected to another area. We also want to look at, obviously tuning performance and comparing with other approaches. We found another approach that was looking at tracks in sort of like a naval setting, and they used a different approach, a kernel density estimation. Our initial attempts found that it was fairly slow, but we want to see if there are other approaches that might apply. And then finally test with DoD data and ultimately transition this to whether it's Project Maven or some other group that might be able to use this with their data. And then, of course, additional pattern of life analysis, anomalous tracks is not the only thing. We can look at behaviors of specific objects, so whether the objects are accelerating, decelerating, or potentially patrolling in an area. Those are all things an analyst may want to know. There's the behavior of once you start looking at how objects interact with each other, then you start to get more emergent patterns, such as are people frequently entering or exiting from buildings, vehicles? Is there some malicious activity going on where they're unloading lots of supplies at a location? Are there convoys or other formations of people forming? And then this last one is techniques to incorporate context. And what I mean there is that whether it's a multi-int data, so you have data from other sources like audio or radar, or maybe it's just the mission plan that for a particular mission, not all missions are the same. And so looking at ways that we can take context, apply it to a particular scenario, and say, in this given context, this may be anomalous, but it may not be anomalous just because of the way that things are working out to be. So I'm going to go ahead and hand it over to Oren, and he's going to talk about emotion recognition from voice.
Thank you, Kevin. Good morning. I'm excited to talk to you today about an ongoing project in what people are now calling machine emotional intelligence. This is the capacity for machines to perceive and understand human emotion and mental state. And over the past couple years, the SEI has been working on a portfolio of passive biometrics projects in this area. In 2016, we built off of research at MIT and Scilab here at CMU to create real-time heart rate extraction with just a commercial off-the-shelf web camera. And, last year we demonstrated micro-expression analysis of the human face. This is looking at involuntary tics and twitches to see if you can tell human emotion. This is a fellow at a professional poker match. He just got a flush. He's about to win, I think it's $1.8 million. I'd probably be pretty happy too. Separate from this research, Dr. Rita Singh at CMU's Language Technologies Institute was approached by the US Coast Guard. The Coast Guard every year deals with hoax Mayday calls. These are expensive to respond to, and they're also dangerous because they take resources away from actual emergencies. And they were getting hoax Mayday calls like this one. Hopefully it's not too loud. They were getting these short, noisy recordings like this, and they didn't know what to do with them. So they approached Dr. Singh and asked her if she could help them with this. And so she was able to apply her voice forensics research and create an entire profile of this guy. She was able to tell what his ethnicity was, what his upbringing was like, his height, his weight, a whole set of features. And I was amazed when I first heard about this. And it was a success. They were able to find this guy, and she's since done a lot of voice forensics work with various groups in the government. She spoke about it this year at the Davos World Economic Forum. And this year we set out to see if we could apply her work to discerning human emotion. So an explanation of why this works, it seems almost fantastical, begins with an explanation of the human voice, I think. Your voice is unique. It's like DNA or a fingerprint, and it's the product of a very complex physical and cognitive process. You are pumping air out of your lungs. You are varying the vocal folds, the tension of your vocal folds. You're changing the shape of your vocal cavity, of your mouth, your tongue, your jaw. You're expelling a time-varying pressure wave between 50 and 6,800 hertz. And every step along the way, the production of your voice is affected by things like your health, your energy, your stress levels, your hormones, and your emotion. So Dr. Singh is able to analyze these voice features, these biomarkers, with a set of techniques that she calls microarticulometry. This is the measurement of voice properties at the phoneme level, and it's made possible by over 30 years of speech emotion recognition and automatic speech recognition technology at CMU. The core idea is that you're taking utterances and words and automatically breaking them up into phonemes. This is the constituent compositional unit of speech. And then with each phoneme, you're analyzing it for fine-grained voice features. So some of the mission applications of a speech emotion recognition system are obvious. Things like security checkpoints and intelligence profiling. But the one I'm most excited about is a little further down the road, and I think much farther reaching, and that's human-machine teaming. Just as a human is going to need to understand and trust the machine that he or she is working alongside, it's vital that the machine is able to understand and react to its human partner. So I don't have time today to go into every step of what we're working on as much as I would like to, but I do want to call attention to what I think are the two key contributions of this work. The first is the creation of a new speech emotion recognition database. Current databases are small. They involve tens of speakers, hundreds or thousands of recordings, and this is quite inadequate for creating robust classifiers. So we're doing something that's an order of magnitude larger, and it's being done in part with crowdsourcing, and we are also borrowing a model from psychology. Instead of using discrete labels like happy or sad, we're working on a continuum of emotions. This is called the VAD model. It stands for valence, arousal, and dominance, and it allows us to map out this spectrum of emotions, which is much more reflective of how we actually experience emotions and affect. The second contribution is the creation of this new speech emotion recognition prototype. This is where Rita's work in microarticulometry comes in. Current approaches, the current state of the art, looks at only broad scale voice features, and it's really brittle for things like noise, which of course you have to deal with if you want a system that will work in the real world. So we're coupling Dr. Singh's work in microarticulometry with deep learning to create a new kind of emotion classifier. So thus far, we've completed a lot of what I think is the foundational work for this project, things like audio segmentation and baseline emotion classifiers. And we're also in the process of hosting data on Amazon's Mechanical Turk service to do some of the crowdsourced labeling for this database. And over the next year, we will, as I mentioned, have created the largest ever speech emotion recognition database, as well as this novel speech emotion recognition prototype. And I'm excited to share the results with you in a year's time. Kevin earlier mentioned the semantic ladder, and I think that's where we want to end today's talk. Machine learning is a capability enabler. It's not the only capability enabler offered by software, as you've seen over the last 2 days, but we think of it as a key capability enabler across pretty much every conceivable mission space. And if a strategic advantage is to be gleaned from machine learning, it's going to come from climbing the semantic ladder here, from going up from perception towards comprehension and understanding and action. Of course, that's only a piece of the AI stack, and that's only a piece of the work being done at SEI. But with that, I think Kevin and I thank you for having listened to us. And if you're interested in contacting us, here's Kevin's information, here's my information. It's available in the slides, and I think we have a few minutes to take questions. Thank you. Yes.
That was very impressive that for that couple of seconds, that 2 seconds of voice that you were able to come up with all that information. Was that a predictive information or that was real information?
So that was predicted. That was part of Dr. Singh's voice forensics work, but all of that information turned out to be true.
Oh, 100%?
100%.
Wow.
I mean, within confidence measures and such.
Okay, so most academic research in machine learning is focused on what academics are used to, which is the consumer market usually.
Yes.
Where obviously you're applying it to DoD problems, which are very, very different. Is this mainly a matter of applying the same technology to different problems, or is there fundamentally new technology that has to be developed because of the different applications?
Yes. So it's a bit of both. It's about looking at what the commercial world is doing, because in many ways they're ahead of defense, but also sometimes the problem spaces are fundamentally different. You're dealing with data where there's way less certainty, it's much more dynamic, it's oftentimes much harder to capture So I think it really is a bit of both.
And just to add on a little bit, coming from like aerial surveillance perspective, if you look at a lot of object detection, classification tasks, you have dogs, you have cats, you have a lot of high quality HD images, and so some of the approaches that may work very well on that kind of data has trouble when you're looking at very fuzzy data with other because it's being sent down from a platform in the sky. You have other irregularities that get put in the data. A lot of times the things you're detecting are very small, and so some of the techniques definitely apply, but a lot of it may be tweaking those techniques and also looking at other types of intelligence that you could bring in to augment that.
Any other questions? So the underlying mechanics are universal across cultures, but how much culture affects, for example, our perception of emotions is an open research question. All right, thank you.